Oh, thank you. I would have forgotten for sure. So it's really great that we have Pierrick back to tell us part two of flow tree formula for DT invariants.
Okay, so thank you. So the second talk will be really about the title, so the flow tree formula for DT invariants of quiver with potentials, unlike the first talk, which was mainly an introduction to the topic of DT invariants. And as I said last time, so this formula was first stated and conjectured by Alexandrov and Pierrick. And in some joint work with Julia Argus, we give a mathematical proof of this formula. So it is what this talk will be about. So before that, I go extremely quickly through what we did last time. So we are considering a quiver, so a finite graph, equipped with a potential, so with a formal linear combination of oriented cycle of the quiver. And we will always work with the following notation. So n will always denote z to the power the set of vertices. So simply z to the power the number of vertices. And I will denote by n plus some of the positive part, the set of element in this lattice, which has non-negative components and not all zero. And so this n or n plus is a place where dimension for quiver representations live. So last time I described what are quiver representations. And a quiver representation has a discrete numerical data attached to it, which is dimension, the collection of integer. And so this integer gamma will live in n plus. On the other end, we had introduced this space MR, which is from n to r. So it is a real vector space of real valued linear form on n. So it's simply r to the power number of vertices of the quiver. And this space is where the stability parameters are living. So for every gamma in n plus, a dimension vector, we consider the hyperplane gamma perp in MR, which is a set of linear form theta, such that evaluated on gamma, they give 0. And we will restrict our stability parameter when talking about representations of dimension gamma to be an element theta into this hyperplane gamma perp. And so given such a choice of gamma in n plus, a dimension vector, and theta, a stability parameter in the hyperplane gamma perp, so we had this moduli space of theta semi-stable quiver representations of dimension gamma. The potential define a trait function on this moduli space. And out of this data, you can cook up a DT invariant omega gamma theta, which is essentially a Laurent polynomial in two variables y and t with integer coefficients. And so some of these refined DT invariants are the thing we care about. They are the output of the data of the quiver, the potential, the dimension vector gamma, and the stability parameter theta. And so they really depend on the stability parameter theta in a non-trivial way. There is this wall crossing phenomenon as far as theta is generic enough. So if theta is a point in the hyperplane gamma perp, which is not in the intersection of gamma perp with another distinct hyperplane gamma prime perp, then as long as you are in the complement of this locus of intersection with other hyperplanes, your DT invariance omega gamma theta is constant. But when you go through one of these locus of intersection with other hyperplanes, if your theta becomes non-generic, then your DT invariant will jump in general. And so last time, I essentially ended by defining the notion of attractor DT invariant, which are essentially for every gamma, for every dimension vector, the corresponding attractor DT invariant omega gamma star is a DT invariant omega gamma theta, where theta is a very particular point inside the hyperplane gamma perp of possible stability parameters. And this very particular point was first approximation, the point obtained by taking skew symmetric form of gamma with something. So in this quiver story, there is a natural skew symmetric form obtained by essentially skew symmetrizing the matrix of adjacency of the quiver. And so if you take this skew symmetric form evaluated on gamma, it is a linear form on n, so it is an element in M. In fact, because gamma is 0, it is a point in the hyperplane gamma perp. And more precisely, the attractor DT invariant were defined by taking theta, a very small generic perturbation of this point. And the point was that in many examples, is attractor DT invariant, the set of attractor DT invariants, so the set of omega gamma star, in many cases is much simpler than the set of all possible omega gamma theta. And this thing is just a small technical point. It will be easier to work with, to state the formulas to work with the rational versions of the DT invariants, which are these omega bar. So I have omega bar gamma theta, which are defined in terms of the omega gamma prime theta by this explicit formula, which can be inverted. So you lose no information if you know all the omega bar, you can recover all the omegas. Okay, and then the shape of the formula, of the flow tree formula, was that you could compute such general DT invariant omega gamma theta, so for any dimension vector gamma in n plus, and any generic stability parameter theta in the hyperplane gamma perp, in terms of the set of attractor DT invariant omega gamma I star, where in this formula, you need to sum over all possible decomposition of gamma into sum of elements in n plus. So for example, the first term of this formula is you have the trivial decomposition gamma equal to gamma. And so the corresponding expression here will simply reduce to the attractor invariant for gamma. Okay, so this formula is telling you the DT invariant omega gamma for the stability theta is equal to the attractor DT invariant, so the DT invariant for the stability at the attractor point, plus correction terms. And the correction terms are indexed by partitions, by decomposition of gamma into sums of other elements in n plus. And then what will be involved are attractor invariants for the corresponding dimension vectors, gamma. So as I was, I guess, saying briefly last time, the fact that there exists such formula with such shape is not really surprising, because you might go to the stability parameter theta, to the attractor point for gamma by following a path. And each time you find a non-generic locus, there will be some wall-crossing behavior. But this wall-crossing behavior is known to be controlled by some explicit wall-crossing formula, either in the form of Joy-Song or Contivis-Sambelman. And then you can ultimately argue that there will be a formula with this shape simply by applying many times the wall-crossing formula. There will be a formula of this shape. What is non-trivial in the statement we want to study is to express the coefficients which appear in this formula. So there will be this function fr theta of gamma 1 gamma r, which is the coefficient in front of this attractor DT invariant. So abstractly applying successively the wall-crossing formula, you can say there exists such coefficient. But the point of the flow tree formula is to give an explicit formula for this coefficient, and which has a particularly nice form. And the particularly nice form will be sum over binary trees. So in this talk, so essentially the first part of the talk will be explaining the statement of the theorem. So what I mean is the precise statement. So how are these coefficients fr, theta, gamma 1, gamma r, how are they expressed explicitly as a sum of the binary trees? So this will take a bit of time, so it will be the first part of the talk, essentially explaining the precise statement. And so this thing will be some kind of recipe to compute these coefficients, which is, and so the recipe of the statement of this formula is essentially due to Alexandrov and Pierrick. And then in the second part of the talk, I will start talking about the tools that we'll use to prove this formula. And I will talk about scattering diagrams. I will review the stability scattering diagrams introduced by Bridgeland. And then only towards the end of the talk, I will say a few words about how manipulating scattering diagrams, you can somehow prove this formula. And this manipulation with scattering diagrams is the main technical content of this paper with Argus. Okay, so to state precisely, okay, so from now on, so the statement is that there exists such formula. And what I have to do is to explain how to compute this coefficient, fr, theta, gamma 1, gamma r. Okay, so these coefficients depend on a fixed decomposition of gamma into gamma 1 plus gamma r. So we fix such decomposition from now on. And it will also depend on the stability parameter theta. And so to do that, I need to introduce some amount of notations. So I try to go slowly, but if at some point you get lost, you should stop me. So these gamma 1, gamma r are living in the lattice n of dimension vector, which is just z to the power of the number of vertices. So to state the formula, it is necessary to pretend that the gamma I are linearly independent. So in general, gamma 1, gamma r are just arbitrary R tuple of elements in n, so they have no reason to be linearly independent. Like the number of R of elements can be much bigger than the number of vertices of a quiver. But we want to pretend that they are linearly independent. So what we do is that we introduce some auxiliary lattice, curly n, which is simply a copy of z for each I between 1 and r. So I introduce curly n, which is direct sum from I equal 1 to r of z ei for some basis ei. So somehow I replace the gamma I which live in n, and which maybe have some relations between them, linear relations. I will replace them by the vector ei, which by construction form a basis of the lattice curly n. And so the relation between them is that there is an obvious projection map from curly n to strict n, sending ei to gamma I. So at the beginning, our object live in strict n, but then most of our construction will live in curly n. So we start by essentially pulling back all our data from strict n to curly n. We add the skew symmetric form on n, and we can just put it back to curly n. And I denote it by eta. So concretely, eta is a skew symmetric form on curly n, such that eta of eij is a skew symmetric form between gamma I and gamma j. And so in our story, we care about the vector dimensions gamma, but we also care about the stability parameter, which live in the dual space mr. And so we introduce a corresponding space for curly n. We introduce curly mr, the space of a real valued linear form on curly n. And so by duality of the projection from curly n to straight n, we get a map that I denote by q from straight mr to curly mr. So somehow our space of stability, where the stability parameters lives, is a real vector space. Now it is inside a much bigger real vector space. And so here we are considering a particular point theta in MR, which is our stability parameter we care about. And I just looked to its image by Q in this bigger space. And I denote by alpha the image Q of theta. Okay, so before we have the data of a skew symmetric form on N, which become a skew symmetric form eta on curly N. And we had a stability parameter theta living in MR, which becomes a point alpha in a curly MR. And so here is just a picture of what can happen in some example if your quiver, let's say, has 2 vertices, and if you have a decomposition, if your vector gamma is 2, 1, and if you look to the decomposition into 1, 0 plus 1, 0 plus 0, 1, so it's gamma 1 plus gamma 2 plus gamma 3, where gamma 1 equal gamma 2 equal 1, 0, and gamma 3 equals 0, 1. And so before I was talking about relations between the gamma i's, for example, the gamma i's can be equal. And so here what we do is that we replace this gamma 1, gamma 2, gamma 3 simply by E1, and here it will be E2, E3. So we just form a base of a 3-dimensional vector space where E1, E2, E3 are just standard bases. And this map P from curly N to straight N is just a natural projection map from this 3-dimensional picture to this 2-dimensional picture. Okay, so now our formula for this function f theta of gamma 1, gamma r will take the form of a sum over binary trees. More precisely, we'll consider rooted binary trees with R leaves decorated by this basis element I've just introduced, E1 to ER. So here is a picture of a rooted binary tree. So there is some root at the top, and the root has a single child. And then after that, every vertex has exactly two children, which is why it's binary, until you arrive at the leaves, which are at the bottom of the picture. And furthermore, it's part of the data that the leaves are decorated by this basis vector E1 until ER. And probably something else I should say, that this binary tree, despite the picture, is really some abstract binary tree. It does not come with a preferred planar embedding. Okay, and then so on this picture, I just have introduced some notation which will be used in the explicit formula I will write down in one moment. For every vertex V, this vertex has a parent P of V, and it has 2 children that will often denote by V prime and V double prime. And because there is no planar embedding in general, there is no preferred choice which one should be called V prime and which one should be called V double prime. But still, we make a choice. And sometimes I will write formulas which look not symmetric in exchanging V prime and V double prime, but it is essentially for convenience. So the formula will sometimes be not manifestly symmetric, but in fact, they will be after some thinking. Okay, so I think the last piece of notation I need is that for every vertex V in such a binary tree, I will denote by EV some element in curly N, which is a sum over the EIs which are attached, which are decorating the leaves, which are below this vertex in the tree. So for example, on this picture, I have the vertex V here, and somehow all the leaves, if I go down the picture until the leaves, and I look to all the leaves below V, I get the leaves decorated by E2, E3, E4, and E5. And so EV by definition is E2 plus E3 plus E4 plus E5. Or equivalently, you can give some recursive definition. EV is EV prime plus EV double prime. Okay, so you should think that all the vertices are decorated by vectors in curly n, which are simply the basis element at the leaves, and then just you take sum each time two edges come together at the binary vertex. Okay, so in the title of the story, there is a flow tree formula. So this thing is a tree story. It's about binary trees. And then there is a flow. So what is this flow about? So there is something called a discrete attractor flow. And to define it, you can define it for any omega real valued skew symmetric form on curly n. So here maybe it might sound strange because I just told you that on curly n I have a natural skew symmetric form obtained by pulling back, so the thing I call eta, which is obtained by pulling back the quivers skew symmetric form on straight n. But here there is a construction you can make for any skew symmetric form omega on curly n. And so this construction is a discrete attractor flow. So what is it? It is for a given binary tree. It is an assignment for each vertex of the tree. So each vertex v of the tree, you attach a point in curly MR. in this kind of extended real vector space of stable parameter. To every v, I will attach a point theta alpha omega tv inside this real vector space. So in other words, this flow story will define some embedding of these trees inside this real vector space. We'll map every vertex to a point. And if you wish, you can just interpolate this construction and map the edge to the straight line connecting these points where the vertex are mapped. So we'll essentially, so this flow story will define some embedding of such a tree inside the real vector space. And it's essentially a recursive definition. So if you start at the root, so you map the root to the point alpha, which I remind you is Q of theta. So theta were our initial stability parameter. Q of theta is the image of this point in this kind of extended space curly M. And so we just set our root to start here. Okay, so here it is where you use the dependence on theta here. It is where the root of the tree start. And then you have a formula which extends this definition. So if you have a vertex v, which is not the root, which has a parent p of v, and if you already know what theta of p of v is, then theta of v is defined in terms of theta p of v by this explicit formula. Maybe I should explain where this formula comes from. So the point will be that each of these points theta v, so the point where the vertex v is mapped, will live inside the hyperplane EV perp inside curly MR. So definitely the initial point, this point alpha by construction, it lives by definition theta was living in gamma perp. So this point where the root mapped live into E1 plus E2 plus ER perp. And so this formula is done in such a way that for every vertex v, theta v will live in EV perp. And so the idea, so what happens is that if you start with a parent of v, so theta of p of v, it lives in E of p of v perp. And then you move inside this hyperplane into the direction given by the skew symmetric form omega. So given by contracting omega with EV. And so this formula, it's exactly, so this point theta v, it is exactly the point in EV perp. It is a point in EV perp, which is on the bad locus where you have intersection with the hyperplane EV prime perp and EV double prime perp corresponding to the children of V. So somehow, if you check this formula, if you apply it to EV prime, here we'll get omega EV prime, which will cancel with the denominator. And here we'll get theta POV of EV prime, and so you get 0. So somehow this point attached to the vertex of the tree, they are exactly mapped to points where you have this somehow a very non-generic locus from the point of view of stability parameters, where you have hyperplane intersectings. So it is where the wall crossing will happen. Okay, but just from the point of view of stating the formula, you can just use that as just some algorithm. It's an explicit formula, so it makes sense. And okay, so you can do this construction for any skew symmetric from omega. And now the key, one key technical point of the story is that we don't want to do that for omega equal to the skew symmetric from eta, which is a pullback of the skew symmetric from of the quiver. We want to do it for omega, a small generic perturbation of eta. And the claim, which is something one needs to prove, is that if omega is a small generic perturbation of eta, then we have some quantities. So mainly these quantities, theta of PV evaluated on EV prime is non-zero. And in such a case, you can make the following definition. You can define some sign by taking sign of these non-zero numbers. So maybe this formula looks a bit complicated. I can just say some words why you want this condition to be non-zero. You see that if this thing happens to be 0, then you have 0 in this formula, and then theta of V is theta of P of V. So somehow your flow will be stuck at this point. You will not move from P of V to V. Your point will not move. So definitely you want to try to avoid this thing to happen. And the claim is that if omega is a generic perturbation of eta, then you can achieve that. So somehow it is a point of going to this bigger space, curly M, is that you can try to do exactly the same construction with straight N and straight M, and run the same story given a binary tree, try to follow this flow. But in general, for the standard quiver skew symmetric form, you will hit some bad situation where you will have vanishing of this quantity. And if you simply try to perturb your skew symmetric form in straight N, in general, there is not enough degrees of freedom to achieve this non-vanishing property. Which is why we go to this bigger curly N space, where you have the gamma I, which become linearly independent EIs, and then there is enough freedom to find a nice generic perturbation.
Sorry, Pierrick, can I just ask? I think I'm just missing something stupid. Did you claim that this thing vanishes? This theta vanishes on EV, or what's the property of this theta TV?
Yeah, so I think I say several things. So I think theta TV vanishes on EV, but in fact it also vanishes, and maybe it's more important, on EV prime and on EV double prime. And because EV is equal to EV prime plus EV double prime, so in particular it also vanishes on EV. So already theta TV lives, if you wish, it lives in EV perp. It vanishes on EV, but it is contained in the intersection with the hyperplane EV prime perp.
But if I plug EV into this formula, the right-hand side vanishes, doesn't it? Because omega is skew. Right.
Yeah, that's right. But then theta PV of EV also vanishes because V is like PV prime. So.
Sorry, why does that vanish? Why does theta of P of V on EV?
Yeah, so somehow it is the vanishing I was talking about, but applied to the parent. So as I said, theta V of EV prime is 0.
Ah, oh, I see. Sorry.
Also.
So it vanishes on both, so then it vanishes on the sum. Yeah.
Yes, exactly.
Thank you.
Yes. Yeah, that's also. So here, yeah, so here we just did the, yeah, so you see if yes is vanishing property for PV, you have the same for V. I mean,
so it vanishes on all the children. It vanishes on all the children?
Yes. And so somehow what we want to avoid is that if you are a vertex, you want to avoid it vanishing on the grandchildren. So somehow you want, if you have in some upper plane, you want it to live in the intersection with the upper plane defined by one of the children, but you don't want it to be also on the upper plane corresponding to one of the grandchildren. You want the intersection between the child and the grandchild to appear at a different place.
Yeah, I get it.
Okay, so this is explicit flow. So you start with your essentially at your initial step T parameter, and then using the skew symmetric form, you move and you attach different points in curly MR to each point of your tree. And then this is slightly complicated recipe that maybe I'll come later from where it comes from to define a sign epsilon TV at each vertex. And it is to be able to define this sign that you need some number to be non-zero. And to achieve this number being non-zero, you need to take omega, this small generic perturbation of the skew symmetric form. Okay, so it is maybe too much technicalities, but will be done with technicalities very soon. So essentially, here is a formula for the function we care about, for these coefficients which appear in the formula. So f theta gamma 1 gamma r, which says that in the contribution for the DT invariant omega gamma theta, what is the contribution coming from the decomposition gamma equal gamma 1 plus gamma 2 plus gamma r? The contribution is a product of attractor DT invariant for gamma 1, gamma 2, gamma r times his function. And the question was, what is this function? And so the point of the flow tree formula is to express this function as a sum over rooted binary trees with R leaves decorated by E1, E2, ER. So the tree, exactly the kind of trees I was talking about before. And each has such a tree as a contribution. And the contribution of each tree is as a form of a product over the vertices of the tree. And each vertex contributes a very simple expression in Y. In fact, it contributes some Y integer given by the pairing between EV prime and EV double prime. So the vectors attached to the children at this vertex. Okay, so this thing is quite simple at each vertex V. You have the children V prime and V double prime. You have vectors EV prime, EV double prime attached to them. You look to their skew symmetric pairing. And then you take the Y integer version of this integer. So this explicit expression function of Y. And so somehow the non-trivial aspect of the formula come from the fact that there is some epsilon in front of it, which is either 0, 1, or -1. And it is a definition of epsilon which involves the flow story, right? Because for this coefficient, and depending on Y, it does not depend on anything, just the tree. And just from the tree and the skew symmetric form, you have this dependence on Y. The flow story is used to define this epsilon, which is only 0, 1, or -1. And it is in this epsilon that the dependence on the step T parameter theta is. Because your flow was starting at the point theta And so according to what is the initial point theta, your flow will do various things. And depending on what it does, epsilon can be 0, 1, or -1. So in this formula, each vertex of your tree has also this epsilon factor. So some of this thing is a formula. It tells you these coefficients you care about. Take the sum of binary trees, then product of the vertices, then a factor which is just like completely universal, just depends on the skew symmetric form and on the tree. And the full dependence on the stability condition is in this epsilon. And this epsilon is determined by this flow story. And somehow to run this flow story, we need to pick this omega small generic perturbation of the skew symmetric form eta, so that this epsilon is well defined.
Sorry, Pierrick.
Yes.
You said something about symmetry. So this does not depend on the order of gamma 1, gamma r?
Yeah, so maybe I should have said, so when I sum over decompositions, there are sum over unordered decompositions.
Thank you.
So it's like, yeah. Okay, so maybe here is an example, the simplest possible example. If you consider Q the quiver with 2 vertices and M arrows between them, so the M Kronecker quiver, and if you take gamma equal 1, 1, so it was an example I was already mentioning yesterday. And if you consider the decomposition of 1, 1 into 1, 0 plus 0, 1, so here you have gamma 1 and gamma 2. So here, in this case, gamma 1 and gamma 2, it's just a simple case where they form a basis of straight n. So you don't need to introduce this curly n. I mean, somehow curly n is just equal, it's just isomorphic to straight n. So you can, in this example, you can forget this like extended story. You can just work naively in straight n or straight m. And then so you can just apply the formula. So the formula is telling you that the contribution coming from this decomposition of gamma and gamma 1 plus gamma 2 is indexed by rooted binary trees with 2 leaves decorated by gamma 1 and gamma 2. So there is only one such a tree, which is drawn here. And again, because it's not planar, so I have, if I put gamma 1, gamma 2, or gamma 2, gamma 1, in fact, it is the same tree. I just can rotate it. It's the same abstract tree. Okay, so in the formula for this function f, there is a single rooted binary tree which contribute. And then if we apply the general definition, so there is this product over the vertices. So here there is, so it's really product over the binary vertices, so the entire vertices. So here there is only one such vertex v in the middle. And the contribution of this vertex v is just some explicit expression in terms of y, which only depends on the skew symmetric pairing between, so in general, EV prime, EV double prime. So here in this example, they are just gamma 1 and gamma 2, which was this quiver, the skew symmetric form between gamma 1 and gamma 2 is just m, the number of arrows between the vertex. Okay, so here in this function, the sum of a tree is reduced to a sum of a single term. And in this single term, there is an easy part, which is just this expression in terms of y. But then, so with the non-trivial thing is this extra epsilon, we need to figure out what it is. And it is for this epsilon that you need to run the flow story. So you will essentially map your tree to the space of stability parameter. So the root will map to the point theta. And then the middle vertex will map to somewhere which is specified by the formula that I have written down before for the flow tree formula. So sorry, for the formula specifying the flow. And you find that theta v is given by a expression. And then if you just apply the formula defining epsilon, you see that this quantity epsilon at the end of the day is -1/2 the sine of θ1 plus 1. And so you see that depending on the sine of θ1, this epsilon will be either 0 or actually -1. And then it reproduces what we knew before, which is that on one side, when θ1 is negative, our moduli space was empty, our DT invariant was 0. So here, because epsilon is 0, this tree has 0 contribution, and so that's it. But when θ1 is positive, this epsilon is -1, so this tree has a non-trivial contribution. And so it has some contribution, which is this expression depending on y times the attractor invariant for gamma 1 and gamma 2. And as I said last time, so for quiver without oriented cycles, the attractor invariant for the basis element gamma 1, gamma 2 are just 1. And so the upshot is that your DT invariant omega gamma theta is just essentially this function of y, and we just recover the Poincare polynomial of the projective space, which is a moduli space of quiver representations we described last time. And it's nice to check in this example that some of all the signs are correct, that you can check that it makes sense.
Actually, Pierrick, in this example, the discrete flow is irrelevant because there's only one splitting. So you actually don't probe this formula for the flow in this particular example.
Yeah, I think that's true. Yeah, that's true in the sense where the sign epsilon only depends on theta for the parent. And so actually you don't need to know what theta of V is. You only know what theta of P of V is.
Exactly.
Indeed. Yeah, so for many purposes, this example is somewhat trivial. And as I will explain in one moment when I talk about the proof, so some of the idea of the proof is somewhat to reduce to this case. So this thing is like the most simplest case of wall crossing, where you have a decomposition into two primitive charges, and then the change of the DT invariant is just this y integer defined by the pairing between these two charges. And so what the formula is saying is that somewhat every vertex of the tree, you have this basic example which is happening. Okay, so from now on, so maybe I should stop. Is there any extra question on some other statement? Okay, so if not, I will say a few things. So what is the point of the work I'm reporting on? This paper with Ria Argus, which is on the archive since February. So we want to prove this formula. And so to prove it, we will, in fact, prove a marginal formula, which is a flow tree formula for scattering diagrams. So it will be some formula which has exactly the same shape and which somehow makes sense in the general context of so-called scattering diagrams. So some of scattering diagrams are roughly combinatorial gadgets, which are first introduced by Kontsevich-Soberman and Gross-Zibert in the context of mirror symmetry. And so the form I will present depend on the choice of the Lie algebra. And some of the flow tree formula for DT invariants will be recovered by applying this general flow tree formula for scattering diagrams to a particular scattering diagrams attached to our quiver context, which is so-called stability scattering diagram introduced in the paper by Bridgel. So here I just introduced scattering diagram in one particular language. So if you have a stret n and stret n plus, so here I'm using notation which has the same notation as the one I was using for the quiver context. And for the story I'm describing now, first, they could be thought as being separate. And ultimately, I want to apply this story both to stret n in the quiver context, but also to this extended curly n. Okay, so if you have n, which is z to some power, you have n plus the positive part inside, and MR, the real vector space of linear formula. And then if you give yourself P in n plus, a finite set, and if you give yourself G, n plus graded Lie algebra, so it's something which has a decomposition Gn indexed by n plus, and the fact that it's n plus graded means the bracket of Gn1 with Gn2 is contained in G of n1 plus n2, and assume that it's supported on this finite set P. That Gn is non-zero only if n is in P. Then you can introduce a sigma P, some cone complex in MR, which is simply the collection of all the hyperplanes and perp for n in P. So I have this finite set P, and I look to all the corresponding hyperplanes in MR. And I will call walls, all these, I will call walls the codimension 1 cones in this cone complex. So all these hyperplanes intersect. And so inside the various hyperplanes, I have various cones, which are defined by the intersection with the other hyperplanes. And I call these things walls. And here, to be clear, there are walls in the scattering diagram language. They are not the wall of marginal stability in the DT context. So the wall, where the wall crossing is happening in DT context, will be at the intersection of the walls in the scattering diagram language. Okay, so we have this wall, and so for every D such a wall, I will denote by ND the unique primitive element of n plus, such that this wall D is contained in the hyperplane ND perp. So here is an example. If I am in rank 2, and P is gamma 1, gamma 2, gamma 1 plus gamma 2, then I just draw 3 hyperplanes, so in this case 3 lines. And so the various walls are, so I have 1, 2, 3, 4, 5, 6 walls, which are the various half lines in this picture. And then a scattering diagram, so there are various ways to present it, but one way which is convenient for our story is to use a scattering diagram as a map, phi, on this set of walls with value in the Lie algebra G. Such that if you have a wall D, then the corresponding element phi of D lives in the piece of the Lie algebra, which is graded by multiple of the direction ND of the wall. And so in particular, your element phi of D of the Lie algebra attached to the wall as an expansion over as a sum of element n multiple of ND of phi D of n, where this phi D of n is an element in the part of the Lie algebra graded by n. Okay, so see if G, our Lie algebra, is nilpotent because our P is finite. If you iterate the bracket finitely many times, you get 0. And so you can consider big G the corresponding unipotent algebraic group. So where concretely the product in this group between formal exponential of element of the Lie algebra is defined by the Becker-Campbell-Hausdorff formula. And so this thing is a definition of a scattering diagram. You just have in a real vector space, you have a collection of hyperplanes. These hyperplanes intersecting are subdivided into various cones. And so to each cone, you attach an element of a Lie algebra, satisfying this restriction on the grading. And so you can cook up the structure from the DT theory of our quiver. So if we fix a vector, a dimension gamma in n plus, so essentially you can restrict for all purposes in DT theory, you can restrict to the set P of elements in n plus, which are somehow smaller than gamma. And then you consider the Lie algebra, which is a so-called quantum torus Lie algebra. So for each n in n plus, you consider some formal monomial z to the n, and you define the bracket between z to the n1 and z to the n2 to be this explicit formula. So multiple of z to the n1 plus n2, and the multiple is this essentially y integer corresponding to the skew symmetric form evaluated on n1 and 2. So this y integer was exactly the expression appearing in the formula as being attached to the vertices of the tree. Okay, so this thing is an explicit Lie algebra. So you do that if n1 plus n2 is in P and you put 0 else. And then you can just view the DT invariants are defining an element in your Lie algebra in some kind of obvious way. If you have omega n theta of yt, you just take this number and you view it just as a multiple of z to the n. You just use this element as an element in this quantum torus Lie algebra. And then, so if you have a wall D, you attach to it the sum over n multiple of nd, omega bar n theta yt z to the n, where theta is a stability parameter living inside the wall. And essentially by construction, if you are inside a given cone, a given wall, then there is no dependence on theta as long as you stay inside this cone. So this thing is well defined. To every cone, essentially you look to what is the value of the DT invariant there, and you just think about this number as defining an element in this quantum torus Lie algebra. Okay, so in this quiver context, you define a scattering diagram which lives in this vector space MR. Now, so at this point, the scattering diagram is just some formal things, some collection of hyperplanes, cones decorated by Lie algebra element. So what is important is a constraining notion of being consistent. So if here I come back to the general scattering diagram story. So if you have a scattering diagram, so your collection of hyperplanes, and if you have a general loop inside this real vector space, which intersects successively various walls D1 to dk at increasing values of the parameterizing parameter, then each time you cross a wall, on this wall there is a Lie algebra element. And so you can take exponential, you have a corresponding element in the algebraic group. And roughly when you go along your path, each time you cross a wall, you look to the corresponding group element. And then you take the product of this group element along the path. And doing that, you get an element in the group big G. And more precisely, there is a sign. So you take the group element or it inverse depending in which direction you go through the wall. And there is some recipe which tells you which sign to put. And now the non-trivial definition is that the scattering diagram is consistent if this group element obtained that way is the identity element for every loop. Okay, so if you just have upper planes and if you put your Lie algebra element on the walls randomly, and if you do this construction, you will take product of group element, and typically the product will not be the identity. If it is the identity for every loop, the scattering diagram is called consistent. And so somehow the point is that the scattering diagram defined using this DT invariant, something I call stability scattering diagram, has this remarkable property to be consistent. And somehow this consistency condition is essentially a formulation of the wall crossing formula, essentially in the quantary Soberman form of the wall crossing formula for DT invariants. Okay, so all these DT invariants, they define element of this Lie algebra, and they are all constrained by the fact that when you take these loops and you take the corresponding product of group elements, it has to be the identity. And so why it's relevant for us? Because so for our flow tree formula, as I said before, that you can argue that there is abstractly a formula which has such a shape if you just iterate the wall crossing formula. So fundamentally, the question is, how does the explicit flow tree formula in terms of sum over trees, how does it interact with a known quantary Soberman wall crossing formula? And so here the way we input the wall crossing formula in our story is by this consistency condition of the scattering diagram. And now the claim will be that for any consistent scattering diagram, if you forget the DT story, but if you just take this abstract scattering diagram setting, and as long as your scattering diagram is consistent, then it is enough to state and prove a version of the flow tree formula, which will express the Lie algebra element attached to any wall of your scattering diagram in terms of elements attached to particularly walls called initial walls. And the definition of initial walls is essentially the same definition as the definition of attractor invariant in the DT story. So we say that the wall D is initial if it contains this particular point, skew symmetric form of ND with something inside T. So maybe I was not fully clear. So in the general story, you have a Lie algebra, but you also have a skew symmetric form. And you ask that if you have a graded part of the Lie algebra corresponding to N1 and 2, which for which the symmetric form is 0 between them, then the corresponding part bracket at the Lie algebra level is 0. And so in this generality, you can state as a version of the flow tree formula. And so I will not go back to a precise version of the general flow tree formula for scattering diagram because it's entirely similar to the version of the flow tree formula in the DT context that I already explained. So somehow the point is that you will have a similar shape of the formula. So the element of the Lie algebra attached to some wall. And so the part in the graded part of the Lie algebra indexed by n will be equal to sum of a decomposition of n into various pieces. And then a sum. So in general, you will have a map which is constructed by an iterated application of the Lie bracket. At each binary vertex of your tree, you will view it as two things coming in and producing something coming out. And at this step, you will apply the Lie bracket. And so when you apply that for the quantum torus algebra, it will reproduce this Y factor. And so as in the DT story, in the general story for scattering diagram, the non-trivial part will be to define this sign epsilon. And this sign epsilon will be defined in terms of a flow in some auxiliary space curly n. So in the general story, you also need for every decomposition, gamma 1, gamma r, you introduce this basis, you introduce this bigger space, and then you can run a similar story and state the formula. So now I will end on how to prove something. So we have a scattering diagram living in a straight MR. And naively, you can try to run the flow story inside straight MR. And so what was the idea? The idea was just to start as your stability parameter theta, and then move in a direction specified by the skew symmetric form. Essentially, you move, maybe it is a reformulation of the formula which is here. You move in the direction given by skew symmetric form with gamma, which is natural because it's somehow just moving towards the attractor point. You start from your stability point and you try to move towards the attractor point. And then when you move along this line, at some point you'll hit the bad locus where like other upper planes other than gamma perp intersect. And here, in general, to know what happens, you will need to apply the wall crossing formula. But in general, on this bad locus where many things intersect, the wall crossing formula in general will be complicated. The point is that the wall crossing formula will be simple if on this bad locus where upper planes intersect, the only non-trivial thing happening is a decomposition of gamma into two pieces, gamma 1 plus gamma 2, where gamma 1 and gamma 2 are primitive. Then in this case, you can just run the definition of consistency to see that the wall crossing formula takes an extremely simple form And you get the contribution to your invariant, which is just determined by the Lie bracket of these two elements. It is exactly the example I was describing here, where you have a simple vertex, where you only have a decomposition into two pieces corresponding to primitive elements. So the idea of the story is somehow to reduce the situation where you do this flow story, you start somewhere and you move, and each time you find a bad locus, it is only bad in this minimal situation, where the only things happening are decomposition of your vector into two primitive pieces. And it is exactly what going to this bigger space and perturbing this Q-symmetric form is doing. So the claim is that when you introduce this bigger space curly n and bigger curly m, then there is a way starting from the stability scattering diagram in straight M to construct a new scattering diagram in curly M, in this bigger dimensional space. And then you apply this naive ID to move inside this bigger space. And the claim is that if you perturb the skew-symmetric form generically in a generic enough fashion, then if you start somewhere in this bigger space and you move in this perturbed way given by this perturbed skew-symmetric form, then when you hit the bad locus, you will only encounter this simplest possible situation where the only thing happening, the only thing which is relevant is the decomposition of your vector into a sum of two primitive vectors. And somehow you need to ensure that your perturbation is generic enough so that this thing always happens. Then when you continue your flow and you intersect further bad loci, then you are still in this ideal situation. And so somehow the tree simply appear from this flow picture moving in the scattering diagram, hitting bad locus. And if this bad locus is as simple as possible, you only have somehow double decomposition, which matters. And this double, then the effect of this very simple wall crossing is captured by the contribution of the vertex. So somehow the point of the whole story is to reduce some of the general wall crossing story or this iteration of complicated wall crossings to a combination of very simple wall crossings. So the wall crossing of the simplest possible form. And the claim is that it is possible to achieve this situation when you go to this bigger space and if you take a generic perturbation of the skew-symmetric form. So I think it is what I wrote in my last slide. So some of the issue is to replace some of this higher valency situation where many things intersect by a simple situation where simple things intersect. And I'm already a bit over time, so I will stop there. Thank you.
Thank you very much, Pierrick. Are there any questions? Let's see.
Yeah, hang on, switch my video on. Hi, Pierrick, thanks for the talk. Can I ask a question? Can you hear me? Yeah, so after you reduce by passing to this curly n,
yes,
I mean you're looking at intersections of walls where you have well, I guess my question is if you look at an n Kronecker quiver, yes, which corresponds to a kind of two-dimensional scattering diagram,
yes,
with primitive walls, there you have a whole bunch of well, for n, I guess, greater than 1, you have infinitely many new walls coming out and interesting DT invariants on these walls.
yes, yes.
How do you somehow stop those showing up in this picture?
Yeah, so the claim is exactly, so to not, the claim is that if you care about your invariant gamma, you only want to encounter a situation where gamma split into gamma 1 plus gamma 2, where both gamma 1 and gamma 2 are primitive. Mm-hmm. So in your example of M Kronecker quiver, it will happen for like the dimension vector 1, 1. And so indeed, computing the invariant for the vector dimension 1, 1 is easy. And so the claim is that the general case, by going to this higher dimensional space, will be reduced to this case. So what I mean is that if you look to the M Kronecker quiver, and let's say you want to compute the DT invariant for 2, 2. So what the formula is saying, you need to sum over all possible splitting of 2, 2 into a sum of vectors. So I don't know.
Okay.
And so, for example, I don't know if I take 1, 0 plus 1, 0 plus 0, 1 plus 0, 1, it's a decomposition with 4 terms. And then the corresponding new scattering diagram will live in a 4-dimensional space. So somehow the auxiliary scattering diagram depends on which decomposition you are looking at. And so the claim is that there is a 4-dimensional scattering diagram in which the computation of this 2-2 invariant after perturbation of the skew symmetric form can be reduced to a sequence of computation which are as simple as the one that you do for the 1-1 invariant.
But okay, but that's the claim, and it shouldn't be sort of obvious that that simplification will
so
carry through.
Yeah, that's also maybe if I stay with this example in dimension 2, if you run the naive flow story in this 2-dimensional situation, you start at the stability parameter theta, and if you just try to follow the flow, you just hit 0, and at 0 it is where the wall crossing formula around 0 is complicated. So the point is that in this 4-dimensional scattering diagram, so you see in dimension 2, I have somehow 2 initial walls, which are like 2 initial lines. And in my 4-dimensional picture, each of the line will split into, I guess, 2 hyperplanes. And so in the new scattering diagrams, we will have something like 4 initial hyperplanes. And the claim is that if you start from your stability point, and if you move, so again, if you move in just using the pullback of the skew symmetric form, you will just go to 0 again, which is bad. But now the claim is that if you perturb your skew symmetric form generically, and you move along this flow, then you will not go directly to 0, but you will first intersect. You will first go to an intersection of 2 of the 4 hyperplanes, but not a common intersection of all the 4 hyperplanes.
Sure.
So the wall crossing here at this point where only these 2 hyperplanes meet is simple.
I guess that's the bit I don't get. I mean, the wall crossing there is determined by an integer, the integer given by the pairing of the primitive vectors against each other.
Yeah, but somehow by construction, so it's true that the wall crossing area is determined by the integer, but somehow we only consider the output, which is a DT invariant, which is somehow 1, 1, which is just the sum of the 2 primitive things at this point.
Sure. Okay, I see that.
So which is why the answer will always be the y quantum integer version of this integer.
Okay.
And nothing more complicated.
Okay. Okay. I think I see. Thanks a lot.
Okay, thanks, Ben. And we have a question from Boris.
Sure.
Pierrick, I seem to remember that in your paper with Julia, you have a different version where you don't perturb the skew symmetric form, but the stability parameters instead. Can you say a word about this?
Yes. So
that's the version
yes,
which is analogous to the work of gross-boundary-dependent CBUS, where you perturb constraints and so on.
yes, yeah. So indeed, so there is a version where I always get slightly confused. Do I need to go to higher dimensions? Oh, okay, to be safe, let me first, so I still go to higher dimensions, still in this curly n, curly m. But there, I no longer perturb the skew-symmetric form, but I perturb the initial point of the flow, so the stability parameter, in this higher dimensional space.
Right.
And then, so you just perturb the initial point of the flow, and then you run the flow with the honest skew-symmetric form. And the claim is that some of your perturbation is generic enough, then you can still avoid some of the bad situations. And you can still reduce to some of the binary trees where each tree, at each vertex, you will have simple situations.
Right, so it's somewhat preferable in the sense that you have to perturb only n parameters as opposed to n square or n minus.
Yeah,
one.
so in fact, I guess I was I counting? I guess at some point. Maybe I was counting.
Yeah, I think you only need to perturb n parameters. And it's more sort of local perturbation of parameters, whereas the perturbing the skew symmetric form is more sort of a global way of perturbing things. And it's a new idea, whereas the second way of perturbation by perturbing the parameters, that result follows as a consequence of the more general way of global perturbation. So in some way, it's easier.
Yeah, but yes, so definitely both versions exist.
Yes.
And depending on the purpose, you can use one or the other.
I should point out there's actually a third version which does not involve any perturbation.
Yeah, that's right. So I guess it was written on some slide, and for time reason, at some point I skipped. So yeah, so there is another formula which was I guess also conjectured by Pierrick and al, and which has been proved by Sergei Mozgovoi, and which does not involve any perturbations, but which involves sum over trees of arbitrary valencies, not necessarily binary trees. And it's an interesting question to somehow understand the precise connection between this formula, which involves a perturbation and is a sum over binary trees, and the formula of Mozgovoi, which is a sum over non-necessarily binary trees, but which does not involve any perturbation.
Yeah, the price you pay with this other formula is that the unrefined limit y goes to 1 is no longer manifestly finite in particular.
Yeah, and so just at the level of general formalism, the formula of Mozgovoi work in a kind of general like associative algebra context, whereas our formula is really phrased in a kind of Lie algebra context. And so at some point, yeah, that's right, which is exactly related to this point that the y limit is not manifest, because to be able to take the y equal to 1 limit in an easy way, you need the y to be combined into this y integer package, which is really the Lie bracket. While if you only have a power of y, which is just what you have if you only consider the associative product, then it's not so easy to take the limit. So yeah, so there is this other formula, and it's interesting, and it's not really understood how to go from this kind of Lie algebra formula to the kind of other associative algebra formula.
Okay, any further questions? Well, if not, let's thank Pierrick again for some 2 beautiful talks. Thank you. And perhaps we could meet 5 minutes late. So let's meet at 20 past. That's in 5 minutes time.